Alright, one of the concepts that we didn't talk about in the video that I'd like to add here at the very end is a topic called Karnaugh maps, and just to show what Karnaugh maps can do for us. Recall that we mentioned when we were doing our circuit realization from earlier, we had two concepts that we talked about. The product of sums and sums of product in order to represent any given output that we would like to receive from a circuit that we're putting together. And so what I have in front of the camera right now is just an output that we would like to receive from a specific digital circuit. And so in this case we have that if we have all outputs being equal to 0, all inputs 0, 0, 0 for our A, B, and C output, we will expect that our output here will be 1. If we have 0, 0, 1, then we expect our output to be 1 also. If we have 0, 1, 0, we expect 0, 0, 1, 1, we expect 1, 1, 0, 0, expect 1, 1, 0, 1, we expect 1, 1, 1, 0, we expect 0, and 1, 1, 1, we expect a 0. If we were to write the sum of products for each of these terms here, or to be more specific, the terms where we have an output of 1, then the sum of products, each of the products here would be A naught, B naught, C naught, and then we'd have here A naught, B naught, and C. And then we'd move down here to where we have our 1 for the output, which would give us now A naught, B, and then C. And down here we'd have A, B naught, C naught. And then for our final one here we'd have A, B naught, and C. So if we were to put together our sum of products equation for this, then we would have A naught, B naught, C naught, plus A naught, B naught, C, plus A naught, B, C, and I'll move this over just a little bit, plus A, B naught, C naught, plus A, B naught, C. Okay, let's just double check, make sure that is correct. Right, and so this would be the equation that we'd end up using in order to recognize our equation from before, or for our equation from this truth table. But as you can clearly see, there's a whole lot of terms, and it would take a whole lot of circuitry in order to make this happen. So what Karnaugh maps does is it allows us to get the same output but with the minimum amount of circuitry in order to do that. Alright, so in order to make a Karnaugh map, what we need to do first is we need to make a Karnaugh map using gray code, and that's something that we didn't talk about earlier. Now what gray code is gray code is a for the lack of a better term, between any consecutive set of numbers, what we need to have is a minimum, okay, of a 1-bit change between them. So if we push the paper out this way just a little bit, if we go 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, then we have 1, 0, 0, 1, 0, 1, 1, 0, pardon me, that becomes 1, pencil broke, 1, 1, 0, and then we have 1, 1, 1. These would be the consecutive numbers for 0, 1, 2, 3, 4, 5, 6, and 7 if we were using 3 bits as we were using above in the example where we had an A, B, and C input. And what you'll notice is, for instance, between here where we have our 1 and 2, there's a 2-bit change, because we go from having 1 in this position to a 0, and we go from having the 0 in this position to a 1. And then also what you'll notice is that when we go between, let's say for instance, these two here, consecutive numbers, we end up with a 3-bit change, which is this one, this one, this one. This goes from a 1 to being a 0, 1 to being a 0, and this one going from being a 0 to being a 1. Okay, so we don't want to end up using that if we're producing what's called gray code, which only allows for 1-bit change in between for consecutive numbers. So in essence, what we're doing is we're recreating, if you will, the binary system such that we have numbers representing each consecutive number, but there's only a 1-bit change in between. Okay, so let's start with just a 0, 0, 0, and that seems to be fine, of course. And then we have 0, 0, 1, and there's only a 1-bit change between there. But as we said, there's a 2-bit change in between here. So if we want to redo the 2 in order to just have a 0-bit change, pardon me, a 1-bit change, all right, what we'd end up having to do is to use gray code. And in order to do that, we'd have to take the 0, 1, 0, and we would use the following method in order to find a gray code representation for the number 2. And so in order to do that, what we'd end up doing is, first of all, we'll bring down the most significant bit, so that remains a 0. And then we use modulo arithmetic in order to find what our following numbers are going from left to right. So we have 0 and 1. When we add those two together, we end up with the number 1. So we bring a 1 down here. We have 1 and 0. When we add those two together, we end up with a 1. And so what this says is that to represent 0, 1, 0, we should replace that with 0, 1, 1. So that becomes 0, 1. Whoops. That becomes 0, 1, 1. Okay? And clearly we cannot use 0, 1, 1 again, so we have to replace our 0, 1, 1 here. And so in order to do that, we take 0 plus 1 plus 1. We bring down the most significant bit again. That stays a 0. We do 0 and 1. That means we're going to get a 1. We do 1 and 1. When we do 1 and 1, that gives us 2. But a 0 is in the 1's position, so that becomes a 1. Just to make that clear, what I'm saying here is when you do 1 plus 1, of course you get the number 2. What we do is we keep the 0, okay, and we eliminate, or we just discard the 1. So our representation for binary 0, 1, 1, which is a number 3, we'll put in that place 0, 1, 0. So that becomes 0, 1, 0 in the place of binary 3. And again, this is in place of binary 2. And if we were to just do that one more time here, let's say for the number 1, 0, 0, which is our number 4. So we got 1, whoops, probably pressing on the pencil a little too hard here. We have 1, 0, 0. We're going to add those up together. Again, we bring down that most significant bit. Okay, we bring down that most significant bit, and that becomes a 1. And then we use, pardon me, not plus, but then we use modulo arithmetic, 1 and 0. That gives us a 1 in that position. Let me erase this just a little bit clearer. We use a 1 in this position, and 0 and 0. That gives us a 0 here. And so then the representation for this number in this case is 1, 1, 0. Okay, and you can clearly see as we're progressing through consecutive numbers, we just have a 1-bit change. Okay, now again, the reason for us, pardon me, and as we're progressing through the numbers here, you see that there's a 1-bit change between any two consecutive numbers. Now again, the reason for doing this gray code, or presenting this gray code, okay, and this is gray code, is because we're going to need this in order to put together our Karnaugh map. Okay, so I have a Karnaugh map that has already been put together, and I'm going to use that here in this case. So for this Karnaugh map, you'll notice that off to the left side here, you have our gray code set up where we have 0, 0, 0, 1, and then this becomes 1, 1. Again, only a 1-bit change in between consecutive numbers, and then a 1, 0. And then we also have our 0 and our 1 here for our letter C. Now those are representing the inputs into our circuit that we're trying to create from the previous truth table, and that truth table was again this truth table. Okay, so if we look at this, if we look at our Karnaugh map, in this box here represents our A naught, B naught, and C naught. This represents, and let me move this paper out of the way here, and this represents our A naught, B naught, C, and this is our A naught, B, C naught. And you see how I'm getting these. It's based off of A being 0, B being 1 in this case, and C being 0. Okay, so that's why we had A naught, B, C naught. And so then this becomes here now A naught, B, and C, and this becomes A, B, and C naught, and this is A, B, and C. All right, and then this is A, B naught, C naught, and this one would be A, B naught, and C, C, correct. All right.